Okay, so let us now take a step back and think about how to mathematically model the first price auction, in particular the behavior of the different bidders, right? Uh, so this will allow us to actually kind of like make a bit more precise some of the intuitions that we had and the discussions we had. However, the analysis soon gets very complicated, and I encourage you to kind of go through this part slowly and take help of the reference book if something is unclear, right? So we are going to be solving this first price auction optimal bid problem under a simple case, right? Where we are going to be talking about only two bidders, right? And each of them have a private value that is independently and uniformly distributed between 0 and 1. Okay, so bidder one's valuation is uniformly distributed between 0 and 1. Bidder two's value is again uniformly distributed between 0 and 1. And V1 and V2 are independent. Okay. So these are the assumptions. Now, what sort of information is out there? So each of the bidders know precisely what their valuation is, right? So it's think of it as a draw between uniform 0, 1, but you only get to see what your draw is, right? So if you're bidder 1, you get to see what V1 is, but not V2. And similarly, from bidder two's perspective, bidder two gets to see what V2 is, but not what V1 is, right? However, the information is common knowledge in the sense that even though you do not see what the other person's true valuation is, you do know that it is being drawn uniform between 0 and 1, right? So that is the information structure that we have. Now, what is a strategy? Remember, a strategy is a function which maps your own valuation to what you are going to bid, right? So for different valuations that you might have, you will have different bidding, right? And the relationship between what you bid and what your valuation is given by this function S, right? So in terms of optimal bidding thing, what we are doing is we are trying to figuring out what should this function S look like, right? So this is, if you think about it, a pretty complicated problem because you are not maximizing over one variable, but you are maximizing over the space of functions that is out there. Okay, so let us make some assumptions to kind of like simplify our problem a little bit. So we are going to assume that S is a strictly increasing differentiable function, right? So what this means is that if your valuation is going up, then you should bid a higher amount, right? So that is the implication of S is strictly increasing, and differentiability is going to help us in trying to make it a problem where you can use the techniques from differential equations, right? The second assumption which we are going to make and which makes sense is that we are not going to actually bid a value which is higher than what our true valuation is, right? Why does this make sense? Because if you actually do that, then if you are going to win, then you will end up with a negative payoff, right? So in that case, that doesn't kind of make any sense. So we are going to actually stick with this assumption that the largest possible value of SV is going to be V. Right? So under these two assumptions, we are going to go ahead and solve the problem, right? Okay, so let's consider the case where we are going to be looking at symmetric equilibrium in the sense that we are going to be thinking of a case where both of the bidders follow the same strategy S, right? So what that means is that they are going to be using this function S, which is the same, right? So if they had the same valuation, then they would have bid the same amount, right? So that is the implication of this, right? What are the other implications? So remember, we assume that S is strictly increasing. So what that means is that a bidder with higher value is also going to bid the higher bid, right? How do we see that? So imagine that you had two bids, V1 and V2, and suppose that V2 was higher than V1, right? So what that means is then you have got the player 2 is going to bid B2, which is equal to S of V2, right? And because V2 is more than V1 and S is strictly increasing, so from there we know that S of V2 is more than S of V1, but S of V1 is equal to B1, right? So from there you end up that B2 is going to be strictly greater than B1 if V2 is more than V1, right? So in words, what this means is that the person who has a higher valuation is also going to produce the higher bid, right? So what's the implication of this? Imagine that bidder I has value VI, right? And because both of them are going to be using the same strategy function S, this means that the probability that this is higher than the value of the competitor is also VI, right? How do we get that? Basically from this assumption that you have got that this is uniformly distributed between 0 and 1. So basically we are asking what's the probability that VJ, which is the other guy's valuation, is between 0 and VI. So this is going to be given by Vi because this distribution is uniform between 0 and 1, right? So what this means is that the player is going to win, remember, if his bid is higher, right? Which from here we know that is going to be the case if his valuation is higher, and this will going to happen with probability Vi. Okay. Now, why is this useful? Because from here we can actually calculate what's the expected payoff, right? Remember, in the first price auction, if you lose, you get nothing, right? And if you win, then you have to pay a price equal to your bid, right? So from here, we know that if you lose, which happens with probability 1 minus Vi, you're going to get 0. So if we are looking at expected payoff, so we have got 1 minus Vi times 0. So that part cancels. But if you win, which happens with probability Vi, you're going to get a payoff which is equal to your own valuation minus what you actually bid, right? So this is this expression which we are calling this function G that tells us what is the expected payoff of a player who has a valuation Vi and is using this strategy S, and the other player is also using this strategy S, right? Okay. Now, remember, we are looking at equilibrium strategy. So if you use the definition of Nash equilibrium, what this says is that for this function S to be an equilibrium strategy, there must be no incentive for I to unilaterally deviate from S when my competitor is also using S, right? That's the definition, Nash equilibrium definition that you have seen, right? So let's kind of like think what are the implications of that. Now, if the competitor is also using a strategy which is given by this function S, right, then clearly I should never bid more than S of 1, right? Why is this the case? Because if you are going to actually bid S1 and win, right, then in that case, you are getting a higher payoff with a bid S1 than you could have got with any bid which was more than S1, right? Why is that the case? Because in that case, you end up going to pay more, right? So in that case, what we get is that you should not clearly bid more than S1. Also, you should not bid less than S0. So what you get from here is that you are going to pay something between S0 and S1, right? So when you are trying to think of if you deviate from SVI equal to VI, then you should do this. Okay. Another thing to note from here is that S0 is going to be equal to 0. How do we see that here? Notice that any bid cannot be negative. So any bid is anyway greater than equal to 0. So S0 is greater than equal to 0. And from the second property, you get that S0 is less than equal to 0 as well, right? So if you combine these two things, you end up that S0 is equal to 0, right? Okay. So what does this tell you? It tells you that if you are going to actually deviate, right, you are going to deviate to a value only between S0 and S1, right? Now, why is this useful? This is useful because this actually kind of like simplifies your problem, right? So initially, remember, we had framed this problem as thinking that you have to choose between different functions S of V, right? Which is a very complicated problem, right? Because then that means that for each valuation, you have to specify what your function is saying. Now, what we got from here, that when you are actually thinking of deviating, right, the only choice is between choosing some number between S0 and S1. What this tells you is basically you can think of this player as, rather than choosing different functions, the player is deciding what to report to this function, right? So either the player can report the true value, which is this VI, right, which will not necessarily result in the bid being VI. We'll see that whether that is the case. Or the player can report some other valuation VI prime, and then the bid will be decided by S of VI prime, right? So instead of playing around by choosing different functions, then the player's problem becomes actually choosing different valuations to report to this function, and then letting the function actually choose a value based on that, right? So this is actually an example of a very complex idea called the revelation principle, which is one of the founding stones of mechanism design. So if this part is not very clear, don't worry about it. Just kind of think that there is some principle called the revelation principle, which converts this problem from a problem where you have to choose between different functions to a problem where you have to just choose between stating what is the value to report to this machine function S that you have, right? So now deviations in the bidding strategy function can be thought about, are we going to kind of like reveal my true value, or am I going to reveal a different value compared to my true value, right? So if I do not want to deviate from strategy S, this can be reformulated as thinking that my payoff from reporting truthfully my valuation to this function S. Okay, this is again different from saying that my bid is equal to my true value, because when I report my value, it goes through this function S and then results in the in whatever bid is going to be decided, is going to be satisfying this property that remember, this was the expected payoff that we had. So the property will be that if I report my true value, right, my expected payoff from doing that has to be greater than if I report a different value, right? In which case my probability of winning becomes V instead of VI, right? And my bid becomes S of V instead of S of VI. So this is my new expected payoff, right? So what this is saying is that in order for this to be a Nash equilibrium strategy, what I require is that my expected payoff from truthfully revealing my true value to this function S, which will give me an expected payoff equal to this, has to be at least as great as deviating to another value to reveal to this function and resulting in this expected payoff. Okay. All right. So, and this has to be true for any value V that I'm going to report between 0 and 1 to this function S, right? Okay. So I want to now think of what value of a function satisfies this, right? So we'll see later using differential equation that the answer is going to be that SV equal to V by 2 satisfies it, right? So before we see that, let's just make sure that this is actually kind of satisfying this equation. So if you now plug in this SV equal to V by 2 here, what you end up getting is that this is VI. This is again VI, but this becomes now VI by 2. So that this expression becomes on the left-hand side, VI multiplied by VI by 2, right? So that is VI squared by 2. Here you have got V times Vi, and this minus S of V will become V by 2. So you have got here minus V by 2, right? So now if you kind of like rearrange, what you will end up getting is that Vi squared plus V squared minus 2 times V multiplied by Vi is greater than equal to 0, which always must be true because that is nothing but V minus Vi squared, right? Which is always a non-negative number, right? So you can do the algebra by plugging in this here and see that this actually does satisfy it. So I'll formally show this using a differential equation, but let's first think about what is the significance of this, right? So notice what was this SV, right? This SV was saying that if your true valuation is V, what should you bid? So this is saying that you should bid a value equal to half of your true valuation, right? So here is the full significance. If both of the bidders know that they are competing against each other and that each has a private value drawn uniformly at random from a 0-1 interval, then it is equilibrium for each to shade their bid down by a factor of 2, right? So basically it is equilibrium for each of them to be using this function S equal to V by 2, right? However, notice this is an equilibrium result in the sense that bidding your own value by half is optimal behavior if the other person is also doing so as well, right? However, if the other person is using any other strategy, then you may have another strategy which will do even better than this, right? So this is not an example where it is a dominant strategy equilibrium to bid your value by shed your value by half, but it is an equilibrium in the sense that if the other person is also doing this, it is optimal for you to do this, right? So this is a weaker result compared to what we had, right? So here we are basically identifying a dominant strategy, right? Not necessarily, sorry, we are not identifying a dominant strategy. We are just identifying a Nash equilibrium. And where did we use this? So when we use this, when we are thinking about what the other person is doing, so that played a very important role, right? So as usual in equilibrium, this behavior and expectations are consistent with each other. However, if for any reason the other bidder chooses to use a strategy which is not this, then your optimal thing may also differ, right? Okay, so where did we get that SV equal to V by 2? Let's take a bit more detailed look. So remember, we had this equation from before, right? That has to be satisfied. So let's rewrite that. So in order for our function S to satisfy this equation, what do we have required? If you notice this, imagine that I write this expected payoff function as a function of V, right? Which is, remember, we had done this here before, right? We had this here, but instead of as a function of vi, let's suppose that we write it as a function of v, right? So we end up looking at this expression here, g of v as a function of v, right? What we want is that this is maximized, okay, by setting v equal to vi. Why is that the case? So suppose you set here v equal to vi, you end up getting this expression that you see on the left-hand side, right? And this has to be greater than any other value of v if you set up here, which is going to give you this expression, right? Okay, so we are saying that we want this function s to satisfy this property that this function g is maximized at v equal to vi, okay? Now, for this function g to be maximized at v equal to vi, we require that the derivative of g at vi has to be equal to 0. Okay, so g prime v has to be equal to 0 at v equal to vi. If you take the derivative of this expression, and you can use product rule, so you end up getting g prime v, okay, equal to, will become vi minus sv minus vs prime v, right? How do you see this? So your first term is v times vi. So if you take the derivative, you end up getting only the vi. So that's the vi here. The second term is minus VSV. So you use the product rule. So you have got minus SV, and then you have got minus VS prime V, which is how you end up getting here, right? So we require that G prime V is equal to 0 at V equal to VI. So set this equal to 0 for V being equal to VI. And then if you kind of like simplify, you end up getting this differential equation. And this has to be true for all VI in the interval, okay? Now you can solve this differential equation and you can show that this will satisfy this, right? Vi plus 2. So one way to see that, at least, to verify that this actually does satisfy this, notice that if this was the case, then the left-hand side will become half, right? Because if S of Vi is Vi by 2, then S prime Vi is just half. And the right-hand side is 1 minus SVI by VI. So if you divide this by VI, this is also half, right? So at least half equal to half. So that means that this is actually consistent, right? But you can also show that this is also from the differential equation. You could have also backed this up, okay? So this is how, more, if you like, a more precise explanation for how did we actually end up this without, guessing what this is, right? So this had only showed here that this satisfies it, but here now I am showing to you why did we come up with that particular case. Okay, all right. So this was for 2 bidders. You can actually generalize this, and you can look up the textbook reference to see how the results generalize, but the same technique is there, so I'm not repeating the analysis. So if you have n bidders, you get the following result that if each of the bidders are drawing their true value again independently and uniformly at random between 0 and 1, then the optimal bidding function in, again, Nash equilibrium is going to be of the form S of Vi is equal to n minus 1 by n times Vi, right? So the previous case that we discussed had n equal to 2, hence this n minus 1 by n had become 2 minus 1 by 2, or half, right? But the general result is that if you have n bidders, this is what you get, right? So this is actually interesting because let's see what happens if we change the different values of n. So we had already seen for n equal to 2, you get that S of Vi is V by 2. So you should shade your value by half. So if your true value is 10, and if all of the players are using this kind of strategy, then you should have bid 5, right? But suppose now your kind of like the number of players go up. So suppose it goes up to 3, then this n minus 1 by n will become 3 minus 1, so 2 by 3, right? So which is more than half. If you have got n equal to 4, then this goes up to n minus 1 by n becomes 4 minus 1, 3 by 4. So again, which is more than 2 by 3. And as you can see, as we keep increasing n, in the limit, this is going to approach 1, right? So what this tells you is that as the number of bidders are increasing, then you have to bid more aggressively, in the sense that you can actually shade your value only by a little bit of amount, right? So you have to keep on increasing the bid as the number of players goes up. And this actually is, something that we had already said intuitively has to be true, but now we have seen a more precise explanation mathematically about why that is true. But again, in this particular case, right? Recall that we've actually made a lot of assumptions. In particular, we assume that this distributional assumption that this bids, these valuations are being drawn independently and uniformly at random between 0 and 1. So if you change the different distribution functions, you can still carry out the same procedure, except that you won't get such a nice neat form, but you can still kind of see how this is done in the textbook if you want to kind of like explore that.